Hi folks, yeah, what a week of ups first of all and then downs regarding Holstein Kiel, of course. What a fantastic, terrifying, in the positive sense terrifying, win on Wednesday evening against Cologne. It was all about us because we were so focused, and then this, how can I say, devastating loss on Sunday. So yeah, the truth is once another year in Liga 2, but maybe next time. So yeah, as always, life goes on. We have to move on. Life will go on, and of course also our lecture will go on. Even though it's hard, I know, but yeah, we somehow have to move on. So we are in the middle of clustering high-dimensional data, as you probably recall, after getting over the hangover. Yeah, we talked about different challenges, of course. Keep in mind especially, or I want to remind you especially about, of course, all the cursive dimensionality stuff, but especially about relevant and irrelevant attributes and the relevancy, or also correlated attributes and non-correlated attributes, and that these relevancies and these correlations may be different for different patterns, for different clusters. Yeah? So that is the basic, big picture here, the basic big challenge that we try to solve. And then we may also have these overlapping clusters, so that things may be in different clusters together with different objects, depending on what kind of features I'm looking at. Yeah, so this is sorry. This is probably the analog one for the baby shape game. Yeah, so that we can group these different toys according to different semantic layers in different groups. Yeah? And we got to know about the subspace clustering algorithms first. Well, the most important, or the basic idea of these subspace clustering algorithms is that they start from one-dimensional clusters to look for higher dimensional ones. Yeah? So the basic assumption somehow is that we see a higher dimensional pattern already in the one-dimensional projections. Yeah? So that is the basic approach. That is the basic idea. Then they start, these methods start from one-dimensional clusters and merge them somehow to higher dimensional clusters. Yeah? So the basic idea, once again, the basic assumption is that a high dimensional pattern, like a four-dimensional subspace cluster in a four-dimensional subspace, is already somehow visible in all the projections of the cluster of this four-dimensional subspace. Yeah? Which makes sense maybe on the first glance, but if you think about it a little bit deeper, it need not to be the case, of course. Yeah. So, since we're talking about clustering, which is puzzle playing stuff, we need to know about the assumptions behind those different methods. Yeah, in order to decide what kind of information they give us, if they give us some results. Yeah? But anyway, those subspace clustering algorithms start with one-dimensional subspace clusters, merge them to form high-dimensional subspace clusters. Most of them, or many of them, we got to know about these monotonicity criteria. So if the cluster criterion or the subspace search criterion is monotonic, meaning that we have this property that if a higher dimensional subspace cluster also is visible in all the projections of this high dimensional thing. Yeah, and the other way around means that if there is no subspace projection or no cluster in some specific subspace projection, any superspace of this cannot contain a cluster also. And that allows us to apply these a priori style bottom-up search, like these item set mining algorithms. A priori is an item set mining algorithm, FP growth or whatever. Yeah? They are basically inspired by these kinds of search methods. We also saw different heuristics if the cluster criterion does not implement the downward closure property, the monotonicity property. Then we need some other things like best first or stuff like that. Yeah, we already talked about here in feature selection that the search space is huge. The search space of all possible subspaces is huge. So we need to somehow navigate through that. And one thing is under monotonicity, a priori style things, and others would be some kind of heuristics like best first or stuff like that. Yeah, we also saw some clustering of base clusters of one-dimensional clusters and stuff like that. One final word about subspace clustering algorithms: they are restricted to axis parallel subspaces, subspace clusters, meaning that they only look for relevancy or irrelevancy of features, not for correlations of features. Yeah? And the same holds true actually also for projected clustering algorithms, which we will cover next year in the remainder of this podcast and all the other podcasts. And we'll also take care about pattern-based clustering algorithms today or this week. We'll see that pattern-based clustering algorithms are a little bit different to this view on axis parallel, non-axis parallel subspaces. We'll see that they exhibit some kind of strange patterns sometimes, but we will discuss that when we come to the point here, and we'll stop afterwards because next week and probably also the week after, Daniel will tell you a couple of things about correlation clustering algorithms, which actually look then for these correlated clusters, correlation clustering, so for arbitrary oriented subspace clusters. So now let's start with the projected clustering algorithms, and once again we still look for axis parallel things like the subspace clustering algorithms, but now we don't search from bottom up but from top down, so to say. Yeah? So the subspace clustering algorithms start from one-dimensional projections and form higher ones, or one-dimensional subspace clusters and form higher ones. And as a side product, we get this overlapping cluster property also, because points may be in different subspace clusters now. Yeah? With projected clustering algorithms, that's a little different because they typically try to do it top down. So they start with the entire feature space and try to somehow decide which kind of projection is the best for which kind of cluster, so to say. Yeah? So let's start with that. And there are many different variants for top-down subspace search, because that is the most important point. Typically, we rely on existing clustering models like density-based or k-means clustering algorithms or paradigms or stuff like that. But the most important point is the subspace search. And for top-down subspace search, not bottom-up as before, we have basically these three different subspace or different variants, different paradigms. The first one is a so-called cluster-based search. We try to learn the subspace of a cluster from the entire d-dimensional feature space. Yeah? So we start with full-dimensional clusters or cluster candidates, and then try to iteratively refine the cluster memberships of points and also the subspaces of the cluster. Yeah? So we talked about in the challenge chapter, we talked about integrating the subspace search into the clustering algorithm, and these are actually doing exactly like that. Yeah, they try to iteratively refine cluster memberships and subspace clusters somehow simultaneously. Yeah? And they start with full-dimensional clusters typically. So that is the cluster-based search. So we have clusters and try to get the relevant features for those clusters, and then refine features, relevant features, and cluster memberships. The second here is the so-called instance-based search. They try to learn for each point the subspace in which this point clusters best somehow. Yeah? So that is the so-called subspace preference of a point. And we still try to learn that from the entire d-dimensional feature space again. Yeah? So for each point, then that is why it's called an instance space. So here in cluster-based, we somehow try to learn the subspace preference of a cluster for the entire cluster. And here with instance-based searches or search algorithms, we try to learn that for each individual point. Yeah? So we try to learn for each individual point which is the subspace clustering or the subspace preference of this point, which specifies the subspace in which the point clusters best, so to say. Yeah? And then if we do that, we can merge points that have a similar subspace preference to generate the final clusters Yeah? Of course, we will, I mean, that is quite abstract right now, but we will see, of course, concrete instances of these subspace search algorithms. And the third one is just a random search for relevant subspaces, yeah, some kind of sampling approach. Could be random sampling or more intelligent sampling, but typically it's random sampling or different random sampling strategies, Monte Carlo, whatever. And these algorithms try to learn the subspace preference again of clusters, like in the first part, or of points from randomly sampled points. Yeah? So those, the upper two here, try to somehow get a kind of local view on the cluster or a local view on the points in the entire, or starting with the entire feature space. And with the random search algorithms, we typically just sample points and try to learn some subspace preferences for the set of points, meaning for a cluster or even for individual points. Yeah? And as I said before, we'll see different approaches in action here, or for all these three approaches, different methods in action.